Hi everyone, and welcome to another Power Electronics class. Today's class, we're going to have a review session for the upcoming exam. I will give you a few minutes after each question to solve the problem. Any students that solves it correctly in time would get extra bonus points on their upcoming exam. So for each question that you answer correctly, you're going to get bonus points on the upcoming exam. So that's going to help you. And depending on the question, it's going to be 1, 2 bonus points. So first question, a single phase voltage controller has an input voltage of 240 volts and 60 hertz and a load resistance of R equal to 20 ohms. For 8 cycles, it's on, and for 5 cycles, it's off. We want to determine the RMS output voltage, the input power factor, and the average and RMS thyristor current. Very similar to what we had in the examples. And again, it's open book. You can use your notes from. And it's a good chance to get extra points. Did you solve it, Tyler? No, not yet. Okay. Does anyone have the answer? Perfect. Perfect, great. Very, yes, close, very close, but not, yeah, exactly. But perfect on the, great job on the A and B. So first we want to find the V out RMS, and V out RMS is Vs square root of K. Now K, as mentioned, is N, which is the on time. Here it's 8 over on time 8 plus 5, which gives us 0.615. Therefore, square root of K is going to be equal to square root of 0.615, which is going to be equal to 0.784. Now, V out RMS would be equal to Vs, which is 240, times 0.784, which gives us around 188. Exactly 188.2, yes. But did you get 188.2 volts RMS? So 188.2 volts RMS. Now the input power factor using this equation is going to be equal to square root of K, which is going to be equal to 0.784. It's part B. And part C, for the average, IM is going to be equal to VM over R. And VM is square root of 2 times Vs over R, which is going to be square root of 2 times 240 over 20. By the way, this is a sine wave when it's on, so it's going to point. So this is going to be 16.97 amps. Now for one thyristor, for one thyristor, and when it's conducting during the half positive cycle on one cycle, IT average would be equal to IM over pi. I want to just double check the equation to make sure. Yep, IM over pi times K, which would be 16.97 over pi times 0.615, which gives us around 3.33 amps. I'm going to write the rest here because I don't have space down there. IT RMS would be equal to IM over 2 times square root of K, which gives us 16.97 over 2 times 0.78, which gives us 6.65 amps. So 3.33 and 6.65 amps. Yep. And if we want to find I out RMS, if it asks in an exam, for example, it's going to be V out RMS over R, which would be equal to 188.2 over 20, gives us 9.41 amps. So this is going to be the output. And the power, our input power, if we ask for that, input power would be equal to K Vs square over R, which gives us 1.77 kilowatts. Where did we get this? Input power is V input RMS over R, and that is equal to square root of K Vs, the RMS. And when you square root that, it's going to be K VS square over R, and R was 20, VS was 240, K is 0.615, now gives us 1.77 kilowatts. Great job. Remind me to give you extra points on. Now, second question, very similar again to the first one, changing the numbers and so on. So a single voltage controller has an input voltage of 220 volts. Frequencies this time is 50 hertz, and the load resistance of 25 ohms. On cycle is 5, off cycle is 7. So N is 5, M is 7. Last time N was greater than M, this time N is less than M. Now, we want to determine the RMS output voltage, the input power factor, and the average and RMS thyristor currents. Thyristor. Did you solve it? What is it? What did you get? Okay. Great. Great. Did you all get these same answer? Okay. Now, again, K is going to be equal to N plus M, which is 5 over 12, gives us 0.4167. V out RMS is going to be equal to Vs square root of K. Vs was 220, square root of 0.416. Square root of 0.416 is 0.645. So this would be equal to 142 volts, almost, RMS. Now the input power factor would be equal to square root of K, which is 0.645. The third source current, IM, would be square root of 2 Vs over R, gives us square root of 2 times 220 over 25 ohms, gives us 12.45 amps. IT average is going to be equal to IM over pi times K, which gives us 12.45 over pi times 0.4167 or 0.4. So it's going to be equal to 1.65 amps. And the IT RMS is going to be equal to IM over 2 square root of K, 12.4 over 2 times 0.645. This is going to be equal to 4.02 amps. And again, if we ask for IRMS, it's going to be IRMS would be 5.68, which is V out RMS over R. And the power, the input power would be 807 watts. Okay. Again, that's using this equation that we had here, KVS square over R. Now, next question. In a boost converter, by the way, these are all questions are from the book. In a boost converter, L is 25 microhenry, and it is operating in DC steady state under the following conditions. Vn is 12 volts, duty ratio is 0.4, output power is 25 watts, Fs is 400 kilohertz. We would assume the ideal components. In a boost converter, the input voltage is varying in a range from 9 volts to 15 volts. For each input value, the duty ratio is adjusted to keep the output voltage consistent. At its nominal value, V with Vn equal to 12 volts and D equals to 0.4. Calculate the critical value of the inductance L such that this boost converter remains in the continuous conduction mode at and above P out equal to 5 watts under all values of the input voltage Vn. And find for the values of Vn, you don't need to find all of them, just find it at Vn equal to 9, 12, and 15. Okay, so 1 point between that would be okay. So at 9 volts, 12 volts, and 15 volts. Okay. Again, the first to solve it gets extra points on their exam. Can anyone solve it? I'll give you a few minutes. Tyler, did you have? No. Okay. Do you want me to solve it? Or you need more time? More time? Okay. What did you get? I was waiting for you. What did you get for the critical value of L when Vn is 12? Very close. What did you get, Tyler? You didn't, okay. So the target, the nominal point here for V out is to be at 20 volts. Again, Vn is 12 volts. And when Vn is 12 volts, D is 0.4. V out would be equal to 12 over 1 minus 0.4, which is 1 minus D. So 20 volts is V out nominal. And in operation, we want V out to be held at 20 volts, while Vn, we want it to be between 9 and 15. Specifically, we said we want it to be 9, 12, and 15. We want to see what the critical inductance would be in each of them. And we want the continuous conduction mode, the CCM, for P greater or equal than 5 watts. Now for each Vn, D would be equal to 1 minus V out, Vn minus over V out. So it's going to be equal to 1 minus Vn over 20, because V out is fixed, but Vn is changing. D for each Vn. Did you write that down? Because I have to open another. Okay. Now for each Vn, again, D would be equal to 1 minus Vn over 20. Let me write it down so we have it here. 1 over minus Vn 20. Now the boundary between CCM and DCM occurs when delta IL is equal to 2IN, and delta IN is equal to VND over LFS, and IN is equal to P out over Vn. And these are for ideal situations, by the way. And we have ideal situations. Change the pen to a different color. I think black would be better. So L critical, we had this in our examples as well. L critical is going to be equal to Vn D over 2Fs In. In Ohm's law is going to be equal to Vn over R. We can replace it. So we can write it like this as well. It's going to be Vn, or we can write it like this as well. P is going to be equal to V squared over R. So we can use these two equations. It's going to be Vn squared D over 2Fs P out. You can write it like this as well. Now let's find the critical value of L critical. when Vn is equal to 9 volts. So D would be equal to 1 minus 9 over 20. Let me calculate again to make sure. Yes. Yes, that's correct. It's 0.55. So this is D for 9 volts. D for 12 volts is going to be equal to 1 minus 12 over 20, which gives us 0.4 or 40. And D for the 15 volts is going to be equal to 1 minus 15 over 20, gives us 0.25. Now, V critical is going to be 9 times D over 2. Fs was what? 400 kilohertz? Yes. Times 400 kilohertz or 400,000 times In. Instead of In, we can find using the second equation, because we can find it using P out over Vn, and P out was 5. So In using this equation, then P out, which is it's critical, it's 5 over Vn. How much was Vn? 9. Gives us 0.55. So point times 0.55. If I calculate this, it's going to be 1.11 times 10 to the power of negative 5. Same way, the critical for when it's 12 volts would give us 1.44 times 10 to the power of negative 5. And the critical value for when it's 15 volts, the input, it's going to be 1.41 times 10 to the power of negative 5. So the maximum, where did the maximum occur in this? The maximum occurred when it was at 12 volts, which is 1.44. Times 10 to the power of negative 5, or in other words, it's 14.4 microhenry. So anything above that will keep the converter in a CCM, or continuous conduction mode. Anything above, greater or above 14.4. To round it up, anything above 15, because we don't have a 14.4 microfarad inductor, we have a 15 microfarad. No, the P out is the critical is the same. It's going to be always the 5 watts. We can put it at 5 watts. Yeah, yeah. But Vn is different, so you would find D and In for different Vns. Okay. So I think we have barely time for another question. So for the same thing, this time D is 0.6 and P out is 36 watts. We want to calculate and draw the waveform. What we want here is we want to find in the exam, I would just ask for these two. We want to find IL average and also IL RMS. So IL average and IL RMS. Don't need to do the reform and everything. So IL average and IL RMS. I'm sorry? D is not changing at 0.6. Did anyone solve it? Okay. So since we're running out of time, I'm gonna go ahead and solve this one. So V out is gonna be equal to d over 1 minus d. D is 0.6 over 1 minus 0.6, which is 0.4 times 12. 0.6 over 0.4 times 12 gives us 18 volts. So the output voltage is 18 volts. DTS is the on time, which gives us 1.5 microseconds. This is the on time. And 1 minus DTS is the off time, which is 1 microsecond. This is just for you to know. It's not part of this question, but you may have it in your exam. So this is the off time. Now, the output current is going to be P out over V out, which is 36 over 18, gives us 2 amps. The load resistance is going to be equal to V out over I out, Ohm's law, and gives us 18 over 2, which is 9 ohms. Now, IL average would be equal to I out over 1 minus D. I out was 2. 1 minus D would give us 0.4, which would be 5 amps. So this is our average current. Yes, it's okay. Now the LMS IL RMS would be equal to square root of IL average power of 2 plus delta IL in the power of 2 over Vn. How much is Vn over Vn, which was 12? Now, to find this, I already have IL average, which is, how much was it? 5 squared plus. I need to find delta IL. So delta IL is equal to Vn d over LFS, which is going to be equal to 12 times 0.6 over the L is 25 microhenry, so 25 microhenry times 400 kilohertz. And delta IL would give us 0.72 amps. Now, this times 0.72 to the power of 2 over 12 would be equal to almost 5.01 amp, or just 5 amp would be okay. 5.01 amp. Okay. That's it for today. We're running out of time. Thank you so much, and I will see you on the exam.